46 ACT questions. And 60% of them are word problems. Okay? So we got to know how to take the math and make it real life. And that happens to be a word problem for it. You know, unfortunately, like if they could always say, solve this equation for f of x, we're like, yes, can do that all day long. But they don't say that. Or if they could say for geometry, solve the hypotenuse of this triangle, that'd be great. But they don't. They say, Joe walked so-and-so north and then such and such east. And then he picked up Jane and then they walked such and such north. How far would he have gone if he would have just gone straight there? Okay? Yeah. We have to know how to decipher the word problems for it. So that's why we will just constantly be like throwing word problems in there because it just helps our brain go, what does that word mean? And that's where all that vocabulary comes into play, where we need to know per means, a division sign. If they're saying each, we've got multiplication. That way we can get those words and make them the math that we actually know how to figure out for it. Okay, so this week I read this quote, be strong enough to stand alone, smart enough to know when you need help, and brave enough to ask for it. So we're all learning as we're going through. All right, so here's just an example. We're going to go back over and talk through just an example of word problems. George joins the gym. Okay, we need to know how much we're going to owe. We're all getting into the place. You guys are getting to where you've got jobs and you've got things that you need to pay for, whether it's a car, insurance, or loans, or your going out money, or those type of things, right? So he pays $25 to sign up. So anytime you have an initial, like if you're working on homework or a test, I'm just going to be like, we can do like initial, or I'll do like start. So that's where I'm starting, right? And then $15 each month. So in this way, we have 15 each as multiplication, month is our variable, okay? So when we can write in what it is, and is addition, subtraction, multiplication, or division? Addition. And. When we can write on top of our words, then we get to see our math that's in there, right? So how much does he pay after 5 months? So they're telling us the X. So we just rewrote it as $25 is where he started. That's our constant. So when we think of it as y equals mx plus b, like there's our constant, this is our starting point. And $15 each month. And then we just fill it in and go 5 goes when x is 5. So when he's had 5 months of it, he'll have paid $75 plus his starting fee and have $100, okay? So that's a good way to just look at it there. Let's look at this one. We like going to movies. You get a gift certificate for $25 to your local movie theater. So here's your start, right? That's the money you're starting. Matinees are $4.50 and evening shows are $7.50. Write and graph an inequality that represents the number of matinees. So we know we've got something for matinees, and we'll call it evening shows Y, that you can't attend. So these movies do what? They cost. Okay. When you see the word cost, you're going to think subtraction. It's taking money from you. Okay, so we're going to have an equation that has subtraction. So there's options where I could go to only matinees, correct? Or I could go to only evening shows. We can combine that where I've got $25, okay, and I'm going to subtract from it however many matinees I want, you know. I could do minus how many evenings, but we want to keep that together in one equation, okay? So if we say I've got $4.50 for a matinee, because we called that X, for each matinee, and $7.50 for each evening show, this has to be less than or equal to $25, right?
Yep.
Because I could say no matinees when matinees are 0. Now I just have my evening cost, right? Or I could say when evening shows are 0, and that erases that guy, I only have my matinees. So we're able to answer these when we have the zeros. This this looks like our standard form, correct? Our standard form gives us what two values? The important values. You can look in your notebook, we should have that, right?
Yep.
I think I wrote on there.
Doesn't it give you both your intercepts?
Perfect, yes. Our standard form, if your linear equation review book is in thing, so our standard form gives us, if you didn't write it on there, we did write about you can get the slope from it as negative a over b, but our standard form gives us both of our intercepts for it. So since it gave us when x equals 0, or the first one when y equals 0, I could go to 3 1/3 shows, so technically I could only go to 3, have some money left over. When x equals 0, I could go to how many, or when y equals 0, down for this one I could go to 5 matinees for it. So we have a couple of different options for it. So again, being able to look at our word problems and decipher what they're wanting us to do is important. So we just write those values in there. Okay? So as we move through, this week we're going to look at linear inequalities. We're going to look at some piecewise functions, and we're going to look at absolute value functions. Okay? We're just stair-stepping. It sounds like 3 different things. It's not. We're just we're taking what we've already learned, we're applying it in a different way. We're going to just kind of peel it apart, look at different forms of it. So when we look at linear inequalities, what I like to say is, in math, we like to start baby, and then we just make it broader, make it bigger. Okay, so when you were in elementary school, you learned how to count on a number line, right? Your numbers were all on one single line. That was it. Okay? So then, at the beginning of chapter 1, we began to address inequalities, and we said x could be greater than or equal to 2. Like that. So greater than 2 without equal meant it was an open circle. When we made it equal to, we filled in our circle, correct? So we went from single points on a line to we spread it and we had a larger range for it. Now what we're going to do is, instead of having a single point, we're just going to make our number line bigger. And instead of having this single point, now we have a line that goes through this, and we're dealing with the entire plane. Okay, so we've gone from a point for geometry to a line to a plane of it, and then we'll move into 3D of it. So again, all the rules work exactly the same, which is great. If we know how to do it as a point on a line, we know how to do it as on a plane for it. So when we say, y is greater than or equal to 5, we know how to graph that. We would put a 5 on there, and we would fill in our circle, and we would make sure that it goes greater than 5.
Yep.
Now we actually have a line. So the first thing that we do is we're going to look at our lines, and we're going to graph our lines that we just went back over, and then we're going to address the inequality of it. Okay, so we're just taking everything that was small and we're expanding it. What it does is, instead of giving us one answer, we now have a range of answers that can affect it. Okay, so in this one, is 3y greater than equal to 5? For y equals 2, does that actually give us an answer? Sometimes they'll say it in this way. Does it give us an answer? Well, we don't know. We'd have to plug in y equals 2. 3 times 2 gives us 6. Is 6 greater than or equal to 5?
Yep.
Yes. So that means this point, y equals 2, is in the solution set. Now, there's a lot of different things that could be in the solution set. It could be y equals 3, 4, 5, 10, 100. All of those are going to give us values greater than 5. Okay? And then if we were looking at things as a graph of it, here we've got 2x plus 3y is greater than or equal to 5. So again, we have 2 variables. We can plug in our numbers. Now our numbers no longer look like a single, because with single variables we need a single number to plug in. Now we have 2 variables, so we need 2 numbers to plug in. When we have 2 numbers, it's a coordinate point. So we have our x and our y on it. So is 4, -1 a solution for this inequality? 2x plus 3y is greater than or equal to 5. We don't know. We've got to plug in the values, correct? So I'm going to plug 4 in everywhere I see x. I'm going to plug -1 in everywhere I see y. And I get 8 minus 3, which is 5. Is 5 greater than or equal to 5?
Yeah.
Yes. So we could say yes, it is absolutely a solution. So mathematically, we just put our numbers in. Graphically, when we look at it, on this, 3y is greater than or equal to 5, we would have to say that y is greater than or equal to 5/3, right? To get y all by itself, okay? What kind of line is this that we just learned? No matter, do I have x values in here? No, I don't have x values in it, which means that I can pick any x value that I want and I still get the same answer, right? So if we were looking at that, if x is 0, y is 5/3. We'll do that as just 2 minus something. There we go. Okay? If x is 5, y is 5/3. If x is -5, y is 5/3. Y is always 5/3. Right? So that is what kind of line?
Isn't it 0?
It's a 0 slope. Yeah, it's a horizontal line with a slope of 0. Because if I plugged in my x value, it would have to be 0x. The coefficient of x is always your slope. Okay, so that makes that go away. So now we're looking at this whole line and going, I need every y value that is greater than this line. Right? So I want y values that are greater than this line, that are bigger. We would be looking at anything up here is going to satisfy this equation. In the same way of this one, we would be able to graph 2x plus 3y is less than 5, and then we're looking for solutions that satisfy that. So look on this one, we've got x is less than 3 is what is graphed here. We are always going to graph our line according to equals first. X is equal to 3. So in this way, we have y is equal to 5/3. That gives us a horizontal line. X is equal gives us what kind of line?
That would be
Vertical.
undefined.
Yeah, it's undefined. It's a vertical line because no matter what y value we pick, x is always 3, right? So we would put it in. The way I like to do is put it in first and then say, does it say it's equal to it? No. So in the same way that a circle was filled in if it was equal, but it's not filled in if it's not equal, when it's not equal, we just erase parts of it. We make it that dotted line. Okay? So exact same rules that we've had whenever we were on a line, now we're just extending them to plane. I have some more examples here. Okay? That's what I'm saying here. We're just going to extend these across. Okay? We're just going to make it bigger. We can do it with 2 variables. We can do it with 3 variables. You know, all the different things. And every single graph that we graph, whether we get to parabolas in different conics sections, and they deal with an inequality, they all work exactly the same way. So we never have to learn anything new. It's always the same for it. So when we graph it, so let's look at this example. Graph y is less than -2 on a line. If I graphed it on a line, I would just put my line, circle -2, and I would go less than it, correct?
Yep.
We're going to go that way. Now, if I say graph y is less than -2 on a coordinate plane, I'm going to now graph the line y is equal to -2. So there's my horizontal line, correct?
Yes.
But it's not going to be filled in because it doesn't have the equal sign. Now, once we have our lines, we ask ourselves, I want y values less than this. And we fill in those sections. A good way is to check a value. Does it look on my graph I've got 0. This is the one you always want to check. 0, 0, right? 0 is easy to plug in.
Yeah.
I've got 0, 0 on this side. Does 0 make this true? 0 is less than negative 2.
No.
No. That means this point 0 is not in the solution set, so you need to shade the other side of the line. Okay? Easy way to check. Check something that you know is true. So if I were to go down here and go maybe negative 10, is negative 10 less than negative 2?
Yes.
Yes. So it should be shaded. It should be within. So those are the ways that we check and make sure we have shaded the right sections. All right, so let's do another one here. If I graphed x is less than or equal to 1 on a line, we would pick 1,
Build
we would fill it in, and we would say that it is less than that. I would check 0.
Yeah.
It looks like I've covered up 0. Is 0 less than or equal to 1?
Yes.
Yes, so it should be covered up. Check. It is filled into that space. Okay? If we were to graph it on a coordinate plane, x is less than or equal to 1, I'm going to use the line x is equal to 1. We always use the equal line first. X is equal to 1. Then I'm going to look at my inequality. Did it say it was equal?
Yes.
Yes, so I leave it solid line. And I'm going to go x value is less than that. So on my coordinate plane, where are my x values? My x values are now on this horizontal, right? So I'm looking less than or greater. On y values, we're going horizontally, basically north and south. When we're graphing x values, we're graphing west and east on it. Okay, so see how our inequalities look different? X values less than 1, I'm going to plug in 0. Is 0 less than or equal to 1? Should he be in the shaded section?
Yes.
Yes, he should be. We have shaded the correct side of our line. Any questions about those? So the important thing as we work into inequalities is that we have to know how to graph our line. If we don't know how to graph the line correctly, can we have the right inequality? No. Okay? And as we move for our next chapter 3 is all about where lines intersect. So again, the base thing that we have to know how to graph every single line that we see so that we can find the correct points where they're intersecting. Right? So we're starting small and then we're just combining everything that we know. We're just stacking our Legos with. Okay? So we already went over this. Open line is not equal to, closed line is equal to. Okay? So if we looked at this one, graph y is less than 2x. Okay? We're going to first graph it as y is equal to 2x. So if I look at this line, we need to be able to answer all of our questions. The slope, the steepness, and what are our intercepts for it, okay? So where's our slope?
It'd be, well, the slope would be 2.
The slope is 2. So is that steeper or shallower than our parent function? We're always going to
Steeper.
compare it. So it's steeper. So it's going to be a higher mountain, right? Where is our intercept? Do I have a y-intercept?
It's the origin.
So my y-intercept is 0, right? My x-intercept is also 0. Does it go through the origin?
Yes.
Okay. When we get into parabolas here in a couple of weeks, you will have to answer these questions for every single one. And I'll ask you, does it go through the origin? Does it, like, we're looking at that, okay? At the end of the lesson today, we're going to look at transformations.
Well, if it goes through 0 for y, it has to go through 0 for x, right?
It doesn't, because it could go there, y is 0,
Oh, yeah.
but it has an x value. It's
Yeah.
just been shifted left to right.
Yeah.
Okay? So,
My
we
brain's
can
not
answer
working.
our questions about our line, and so now we can graph our line. It goes through the origin. It's steeper than my parent line, so I'm going to go up 2 over 1, right? So it might look like that. I'm going to draw it straight through. Now I'm going to go back to my inequality. Was my inequality an equal to?
No.
No. So I do not need
need to be
A straight
dotted.
line. It has to be a dotted line.
Yeah.
Okay? I have no problem with you drawing the line first and erasing it out. Whatever. Like if you can look initially and go, it needs to be dotted, but these are the steps that we're walking through. So dotted line first. Okay? It's going to be open it for that. So now we've got to figure out which side of this line do I shape. I need y values that are less than. I like to look at it two different ways. One I showed you, pick a value underneath. We can't pick 0 in this case, okay, but we could pick maybe -10. Does that look like it's on this side of the line? Or +10, okay? So is +10 less than 0, because I'm doing x equals 0? No, it wouldn't, so this guy isn't in there. Is -10, if I pick down here, -10 less than 0? Yes, so this one should be in it. Okay. Another thing is to put a point on your line and think about what they're asking, because sometimes they're asking x values, sometimes they're asking y, and so we're going to address it both in here, okay? If I had this, y is less than my line 2x, I've already drawn my line 2x, so I can label this as 2x, if I label my line. For this point, I want a y value less. Y only goes vertically, up and down. So I'm going less than that point. Okay? Does that make sense?
Mm-hmm.
So if I'm going here, I want a y value less than that. I'm going down from that. Now, if this has an x equals, or an x is less than, and I have drawn my line and they're asking me about x values go left and right. So now I'm going to take my point, and where are my less than x values?
Yeah,
Negative.
on the left.
So now I'm going to go in x value less than, and I would actually shape
Shade
this
that
section.
Instead of, yeah, okay.
Okay? And an x value greater than is going to go that way.
Mm-hmm.
So it changes the place on the line that you're shading depending if they're asking x or y.
Mm-hmm.
Okay? So we can just think through where would an x value be and use that point for it. Okay? So this was the check for those. So let's look at this one. 2x minus 5y is less than or equal to 10. So the first thing that we need is to draw this line. Two ways that we can draw this line from here. It is in which form?
Standard.
Standard. So standard form gives us
The intercepts.
both intercepts. So we could say when x equals 0, so here's my y-intercept. When x equals 0, y equals what?
-5. Wait, when x equals 0,
Uh-huh.
it equals wouldn't it be -5? Oh, it'd be
10.
negative the 1/2.
10 divided by -5.
2. Okay.
-2.
Yes,
You don't divide it by 10?
Well, I'm trying to get y by itself. Remember, y wants to
Oh,
be
yeah.
used by himself. Okay? And then I can answer when y equals 0. So this gives me my x-intercept. When y equals 0, x equals 10 divided by 2,
so
5. Okay, so I have these 2 points, and I can graph 0, -2, and 5, 0, and give myself a line that goes through. We could also change it into slope-intercept form, right? And solve for y. So when we solve for y, we move the x over. So then I would have -5y is greater than, or we solve it as an equals, is equal to -2x plus 10. Then I'm going to divide by -5, right? Divide everything by -5. And get 2/5 x minus 2. So here's our slope-intercept form, okay? Which tells me my y-intercept is -2. I go here. My slope is 2/5. Steeper or shallower?
that would be
Two for-
Shallower. Is it positive or negative?
that one's positive.
still positive, so we're still going up. We're going uphill, just not very a lot. Like we can bike up that guy. You know, we want to run up this one. So we could start at -2 and go up 2, 1, 2 over 5, 1, 2, 3, 4, 5, and graph it that way as well. 2 different ways that we can graph it. Doesn't matter. We're going to get the same line both ways. So now that we have our line, we're going to draw our line between our points, and look at it, and it says equal to. So I'm going to have a solid line now that it's equal to. Now, the thing that's different about this one is when we started in standard form, what is our inequality? Greater than or equal to, or less than or equal to?
Less than or equal to?
What is
Or
this?
greater than or equal to?
Greater than or equal to. But when I moved it to my slope intercept, we did because we divided by a negative. What is my new sign? Less than or equal to. When we graph our inequality, we cannot graph according to our standard unless we're using it to plug in those values, like plug in a point, okay? We have to graph according to our slope form. So now I've got y's are less than. So if I pick a value, I want y values less than it, and I would shade underneath, okay? If I went according to this one and I said greater than, I'd be shading the wrong side of it. Now, we can use the standard equation to go, I have this point, 0, 0 as the origin. Is it a solution or not? Now that I can plug into here. When x is 0 and y is 0, and that gives me 0 minus 0, right? So is 0 greater than or equal to 10?
No.
No, it is not. So this guy is not a solution. So I would need to be shading the other side. Okay. So you can use the standard form to check a point. We cannot use the standard form necessarily to decide which side to shade, because if we had a negative, it would have flipped it. Okay. So make sure that we are looking at our inequalities according to our point slope form. Okay, does that make sense for graphing those? So on your homework this week, we're just drawing lines and making sure that we're shading the correct side of the lines of it for 2.6.
Will there be word problems?
I'll have to look at that. I don't think there's any on this one. If there is, I can send an individual video and address it. Now, what does it look like with the word problem? Okay? What it looks like with the word problem, let's go back, is if I said, similar to what we did for that matinee, for the movies, one is we're going to find out what is our line when it's equal to. Okay? And so if I had the movie one was an exact word problem of it. Or I have so much and I'm spending to buy Christmas gifts that are coming up. How much could I spend up to? Well, you can't spend more than you have. You know, so if we're spending stuff, we can't spend more than we have, but we could spend up to that. So I could spend less than or equal to $100. I could spend 90, right? So we're going to use those things like candy costs this much, so there's our variable, and Coke costs this much. How many packs could you buy together? Well, you can't spend more than that, but you can spend less than that. Or if you say, I have to have at least amount, if it says at least, we're looking at greater than or equal to. Right? Because you can't have less than that. I need at least 10 sets of gifts for my class. For in here, I need at least 2 copies of papers that I come in with. Because otherwise, someone's missing out on something for it. So, at least is going to give us a greater than or equal to. At most is giving us a less than or equal to. So those are these are the vocabulary words that we hear to set up our inequalities.
Okay.
So we're setting the whole equation up exactly like we do with a regular linear equation with an equal sign. We're just replacing the equal sign with a greater than or a less than because we've got a range that we can work in.
Okay.
And these are the two terms that you're going to typically hear, at most and at least.
That works.
So, 2.7 is piecewise functions. Now, piecewise functions can feel like it's something totally different. And oh my goodness, now we're learning a whole entire new concept. It's not. Piecewise functions are taking how we know to graph any line. In this case, we're only dealing with lines. We're not adding conics in there, quadratics, okay? So we're doing lines. And then we're saying, but I don't want all of it. I just don't want all of it. I only want part of it, okay? We're going to make the whole thing and then decide which part that we want. It's kind of like your mom making all of dinner and then you choosing which pieces that you want to put on your plate, right? It's all available. We're just saying, I want this. And it might look different for different kids that come in your house, right? If we have a taco bar, like you might take tomatoes, but your sibling might not. And so depending upon who you're talking to, their plate looks different because they've grabbed different parts of it. So the same thing is with piecewise. We're going to have this whole set of equations, this whole family of equations, and what happens on that graph depends on who you talk to. That's all it is. So we've got to decide who are we talking to and what are their rules. Right? So with piecewise functions, we're not going to use the whole graph. We're going to put restrictions on it. It's written a certain way. Okay? So we will look through the restrictions. So again, we're learning a little bit of vocabulary. We're learning a little bit of like how you actually have to read the instructions for it. Okay? But we're only wanting a certain section. So let's look at y equals 2. I've graphed it right here. So I've got the line y equals 2. It's a y equal 1. It's horizontal. I have no slope, right? So no matter where I'm at, I've got y equals 2, but I don't want the whole line. I only want the section between -4 and +4, which means that I erase all the rest of this. So now I have a segment instead of a line, if we're going to add some geometry into it, correct? So the way that I write it is I write y is equal to 2. So I tell you what my line is. This is the whole thing. And then I tell you which part I want. So x values between -4 and 4. All right? Now, remember, we can rewrite y as f of x. Same thing. It's just a different name for it. It means the function of, and it's telling us which variable that we are addressing. When we have it as f of x, it makes it a little easier to see that when f of x is equal to 2, when x is between -4 and 4, these are the x values that are allowed to be plugged into this equation. Right? So, two different ways to write it, it means exactly the same thing. Okay? Now, when we have more than one, the whole thing is written with these brackets. So we have f of x, which is our other name for y. Okay? So y is equal to, or f of x. So now I have two different lines, two different things. If I am talking to any x value less than or equal to 1, I will use 2x minus 1 as my options to plug in for what my y value is. If I'm talking to any x's greater than 1, I'm going to use 3x plus 1. So let's see what that would look like if we're actually to plot some coordinate points. Okay, so if I have a little, we'll do our little t-chart. I'm going to pick values greater than 1. So if I pick 1, then I'm going to plug 1 into here. So this would be f of 1 is equal to 2x minus 1. This tells me wherever I see my variable, plug it in. 2 times 1 minus 1 gives me 1. If x is, let's plug in 5. Oh, we can't plug in 5. 0. We're going less. 0. I'm still using 2x minus 1. Then y is equal to
Negative 1.
negative 1. Okay. If I picked x is negative 5, I'm going to use this one. And I would get 2 times negative 5 minus 1 gives me
Negative 11.
negative 11. Okay, so there's some coordinates that I have there. Now, if I decide that I want some x values greater than 1, I can't use 2x minus 1. He's got to talk to this guy. So when x is 2, y is 3 times 2 plus 1,
7.
7. When x is 5,
16.
16. Okay? So we have 2 different sets of coordinates that we would be able to plot. We could plot all of these on a coordinate plane. Okay? So we have, since we have 2 different parts, the way that we do that is we go ahead and plot what our lines say. So for part 1, we're going to plot our y equals 2x minus 1. Okay, this is in which form? Standard or slope intercept?
Slope intercept.
Okay, slope intercept. Okay, so our intercept is what?
Negative 1.
Negative 1. So I'm going to go down here to negative 1. When x equals 0, y is negative 1. My slope is 2. It is positive or negative?
Positive.
Positive, steeper or shallower than?
Steeper.
Steeper. Okay, so my line should, so we're visually thinking, what does my line look like? It goes up, it's steeper than my parent function. So I'm going to go up 2 over 1, up 2 over 1. Here's my line. Okay, that's what I'm graphing. However, I don't want this whole line. I only want the part for all of my x values that are less than or equal to 1. So where I find my 1 right here, this is kind of my cutoff, I'm going to erase the rest of it, right? So we only have this lower section.
But the lower section goes forever.
It goes forever, yeah, we've got a line on it. And is my dot at 1 filled in or open?
Filled in, because it's equal to.
Because it's equal to. Perfect. Okay, now, I have another part. This isn't the whole graph of this function because we have another part. What about the ones that are greater than that? Okay, so if we graph this, y equals 3x plus 1, slope intercept, what's my slope?
Slope is
3.
3. It's positive 3. It's steeper, correct?
Yep.
What is my intercept?
No
1. So I'm going to start at 1. I'm going to go up pretty steep, up 3, 1, 2, 3, over 1. And then I could go down 2, 3, back 1. And I've got my line that goes all the way through. There's my line that I want. Do I want the whole line?
No.
No. I only want to deal with values greater than 1. So I'm going to find my 1. And I'm going to erase everything behind it. Okay. Now I'm going to address my circle. Should it be open or closed? It's greater than 1.
not equal to.
So it's not equal. So I'm going to have an open circle right there because it's not equal to it. But then it goes on. So now we get to combine both of them onto the same graph. So for my part 1, I start at 1 and I go down. And sometimes, I like to go ahead and label it. Like this guy is 2x plus 1. Or 2x minus 1. Okay, so that's the equation for that line. Part 2, I'm going to start with my open circle and I'm going to go up. And this guy is 3x plus 1. Okay, and it makes my entire graph. So now if I say, where was my value when x is negative 1? When I'm looking at it, I would go to negative 1 and I would find where it's touching the graph. And I would see that it's down here on this one at negative 3. Okay, so when we're reading the graph, like if you're given a graph that's piecewise and they say f of 5 is equal to what, you'd have to find 5, right? Because this gives us our x value. And then go, oh, it's going to be up here on this graph. This is the one that I'm going to use. It's going to intersect when x is 5, I'm touching up here at 16. Okay? So we're just taking the lines that we already know how to graph, and we're combining them, kind of breaking them up a little bit, and there can be as many as we want on it. Okay, let's look at this one. Okay, so this is a, no, okay. We're gonna look at our piecewise function here in a minute. This is a note that I do have for you guys that you can print out at home as well and fill in these, but we're gonna look at a couple of examples for it. So, in this case, given f of x, let's change that, just do it x minus 1, okay? If x is less than or equal to 2 and 5x plus 3 if x is greater than or equal to 2, we want to find each value. So in this case, when f of negative 5, which equation do I use? This is where we've got to figure out which equation I'm going to use when x is negative 5. So f of negative 5 is telling us this is our x value.
Wouldn't it be the first, since it's less than?
Yes, so negative 5 is less than negative 2, so we use this one, and we would do negative 5 minus 1.
Which would put us negative 6.
Negative 6. Okay? Now, what about f of negative 2? Which equation do we use?
It'd still be x minus 1.
You think so?
It'd be, wouldn't it be
Oh.
5x plus 3?
Never mind.
Or wait,
When
wait.
it's negative 2, can I use this top guy? Because it's less than negative 2. Does
So
it mean
it
it,
can't
is
be.
it when it's equal to?
No.
No, we got to find the one when it's equal to.
So
That would be the second.
So now I have to plug it into the second one. So 5 times negative 2 is negative 10 plus 3,
Negative 7.
negative 7. Okay? F of 7, do I use the top or the bottom?
The bottom.
The bottom, because 7 is greater than negative 2. So we're just figuring out which one to use. So we plug it in. We have 5 times 7 is 35 plus 3. It's going to give us 38. Okay? So when we see it numerically on here, we have to decide which one to use based upon the values that they give us. Okay, so let's look at this one. This one gives us 3, which is fine, right? It's just telling us which part of it. Basically, we've got a couple of different sections. So if I were to look at my x values, I've got stuff that's less than or equal to negative 4. So that's kind of a break. I've got between negative 4 and 1. So I kind of have this section here, and then I've got things that are greater than 1 that
or
way.
equal to.
Greater than or equal to, right? So if I'm looking at it, this is kind of how I would break up my graph. I've got 3 different sections here, so we've got to decide where we're falling. We've got g is g of 2. Does it matter that it says g of x?
No.
No, just labeling graph. It just means the function of 2. So we've got to find out, where does 2 fall? Number 1, 2, or 3?
Wouldn't it be 3?
No.
3.
Well, since
2
it's
is
greater
greater
than-
than or equal to 1?
Yeah.
Yeah.
Yeah. So he falls in this one. So we had plugged 2 into x here. 2 cubed is 8. 8 times 2 is 16. 16 plus 9,
25, sorry.
25. All right?
Yeah.
So now, g of negative 1. Which one of these, where does negative 1 fall? An x value of negative 1.
Wouldn't it be the first?
Is negative 1 less than or equal to negative 4?
No.
Okay.
No.
So it's not that one.
It'd be number 2.
Good guess. All right. Is negative 1 negative 4 is less than negative 1, which is less than 1? Does it fall in that section?
Yeah.
Yeah. Okay. Great. So now we're going to plug in negative 1 here. Now in this case, it's important to use our parentheses, right? because I've got a negative x, so I've got a negative of a negative 1 minus 1. What happens with the negative of the negative 1?
It's positive.
It's positive. So 1 minus 1 is
0.
0. Excellent. Right? Let's do the last one. Negative 6. Where does negative 6 lie?
It would be. That would be the first because it's less than negative.
So it has to answer perfect. Negative 6 is less than or equal to negative 4. Yes. There's our answer. So we would plug in negative 6.
It'd be negative 3.
So I had negative 3 plus 3.
0 again.
It's also 0. Okay? So we've got a couple of things, you know, where we've got some lines where it's crossing on the same parts. Okay? So that is how we are going to plug in whenever we are given our values on piecewise functions. Okay? So we're just looking which one does it satisfy, and we'll just use that guy. Right? We're just looking at the parts of it. Okay? So now, if we had to graph them, same thing. Now we have two different ones. We've got f of x, or we've got y. We can break it up in our two different equations. So this one we have y equals x. This one we have y equals negative 2x plus 1. Okay? Y equals x is what?
Just 1. Well, y equals 1.
Is this the parent function for a line?
Yeah.
Right? So we know that's a 45 degrees straight through everything, right? There we go. Whoop.
That fly.
That fly. He does not want to leave, does he? Okay, so y equals x. Now, do we use the whole thing of y equals x? No, we're only using it for values.
Less than or equal to negative.
Okay, so I'm going to find negative 3 here. 1, 2, 3, and I'm going to go down there, and I'm going to get rid of the whole rest of my line.
Yeah.
Okay? So here's my y equals that x line. Right? Now we're going to graph the next one. What's my slope?
Negative 2.
Negative 2. So he's going down, right? Steeper or shallower?
That's going to be, well,
Are you going faster down the hill or slower down the hill?
faster down.
Faster. Yep. So it's still steeper, but it's downhill.
Negative.
Okay. My intercept is
1.
Yep, when x equals 0, so we cover it up. When x equals 0, y equals 1. So I'm going to plot that and then go down 2 over 1. Down 2 over 1. Okay? So there's my line. Okay, do I want all of that line?
No.
No, we're going to find our
Anything greater than negative.
point. So we're going to find negative 3. We're going to find out where does negative 3, oh, it hits up here. That's where he intercepts, and I want everything greater than that, so he has to go away there. Right? Now, I filled in the circle for this one because it was equal to. We left the circle open for greater than negative 3 because it's not equal to, so his circle gets left open. So now we have our piecewise graph. We have our two different parts. We could say, if I wanted to know, if x is 0, I could go to my graph and say, if x is 0, y equals 1, according to the graph. I could also say f of 0 and find which one of these satisfies for f of 0, top or bottom. So on my graph, I'm looking when x is 0, y is 1. Where does 0? Does it satisfy less than negative 3 or greater than negative 3?
Greater than negative.
Greater than negative 3. So I plug it into this one. Negative 2 times 0 is
0.
plus 1
1.
equals 1. So I still have when x is 0, y is 1. So graphically, I was able to find that it's at 0, 1. Algebraically, I'm able to find that it's at 0 and 1.
Yeah.
Both ways. Okay. Now, domain and range. We get to tie those back in, right? What is domain? X values. Perfect. So all of the x values that are used up, which is great whenever we see it on the graph. What x values are used up? From left to right, what x values are used up with this graph?
Wouldn't it be everything less than 1 or about 1?
Well, if I put an x value here, can I find a place on the graph?
Yeah.
So anywhere I pick on the x-axis, am I going to be able to find a place on the graph?
Yes.
Yes. So our domain values are
everything.
all reals.
Yeah.
Remember we write all reals with that R with the double line? And we say it, we put it in set notation, so that has the little brackets for it. So our domain is all reals. Now, what y values are used up? Do I use everything on my y? Do I use anything above when x is -3, when it's equal to it, y is, well, we'd have to go, right? So it approaches 7, right? But it doesn't exactly hit it. But, so do I use anything above 7 for my y values? No. Do I use all my y values below 7?
Yes.
Yes. So we would write that y less than 7. Okay? Sometimes you say it this way, y for set of y's for y less than 7.
Okay.
In that case. Why did I not say less than or equal to?
Because it doesn't fully equal 7. And it's, well.
Now, if this circle was filled in, could I say equal to 7?
Yes.
Yes. But this gets so close to it, but it doesn't ever actually touch it.
Yeah.
So we can plug it in as if it was equal to actually get that value, but when we notate it, we say it's not equal to. Okay? So we write it our y values for any y less than 7. Those are all of the y's that we use within our graph. Okay? So let's do this other one underneath. Okay? So we have two different ones. So we've got y is equal to -3x minus 7, and y is equal to -5. Right? Y is equal to -5. How do we graph that?
It'd be a horizontal line.
Perfect.
So you go down -5,
1, 2, 3, 4, 5.
and then you go all the way from left to right.
Left to right. Perfect. Well done. Okay. Now, do I want the whole line?
No.
Okay. What is the point that I'm interested in?
Greater than or equal to
-1. So I'm going to find -1. I'm going to find my spot on that line at -1. Okay. I want only the things that are greater than or equal to it. So I'm going to fill it in. And I'm going to erase everything less than. Okay. So that guy is taken care of. Okay. Let's graph this one. What's my slope?
-3.
Negative. So he's going down. Steeper or shallower?
Deeper.
Steep. So he's going down pretty steep. So visually, we need to make sure that what looks like on the graph is what we know it's supposed to look like. If we get a line that looks like this, we've graphed something wrong, right? So that's the whole point. I want you to always be asking those questions. So I asked them, I want visually you to go, I know what this is supposed to look like, so that when you plug in your values and you actually put it on a graph, when you're like, it's not supposed to look like that. You can notice and go, I must have done something. I either switched an X and a Y or whatever.
Yeah.
Okay? So steep, going down, where's my Y-intercept?
-7.
-7. So we're going to go, this one's so hard to see. 1, 2, 3, 4, 5, 6, 7. And I'm -3. I'm actually going to go backwards. I'm going to go up 3, 1, 2, 3, back 1, up 3, back 1. So there's my line. He's really steep going down. Is that what he's supposed to look like?
Yes.
Yes. Okay. Now, do I want all of these values?
No.
No. So again, I'm looking at y equals to -1. So I'm going to find -1, and I'm going to find that guy somewhere right here. Right? He's a little bit lower than that. He's around. about right here-ish, right? And I only want x values less than it. So the ones that are above, I'm going to erase. Okay? It's like a 95-degree angle if we were connecting them, right?
Yeah.
So graphically, this is where we're looking at that. Okay, so what domain? What are my x values that I use?
Everything greater than -1? Or
Can I pick any x value and have an answer? So ask yourself, if I
guess,
pick
yeah.
negative 100, is there a place for me to plug that in?
Yeah.
Yes.
It's here. If I pick positive 100, is there a place for me to plug it in?
Yes.
Yes, so I can pick any x value.
Okay.
So my domain is
It's just
all.
y value that you can't pick anything.
Typically, our domain values are always going to be all rails. Okay. Typically. Depends. Okay. My y values are what?
Anything, is it anything greater to, or greater than, or equal to -1? It's it's not -1. It's
What is that?
-5.
Negative 5. Perfect. Y values for all y's greater than or equal to -5. Excellent. Well done. So visually, we're taking up all the space on our graph that's bigger than -5. No. I didn't realize there was an upstairs.
They working on the roof or
I
something?
don't know. Do something. Okay. Piecewise, does that make sense?
Yes.
Okay. So as we're going through, be sure that we can graph each section, whether it's 1, 2, or 3. Now, what you have, let's look at your piecewise one that's on here, your little packet that I gave you. Try to see what time it is. Okay. You have your first sections. You're actually going to graph them on there, right? Now, keep turning. On A, B, C, and D on the very last page, they just give you the lines. So how would we graph that? I'm going to snag this just a bit and put it up there. Let's do A. So A shows we are at, put 2, 3, oops. So it gives you something like that, right? So how many equations are you going to have for that A?
Just 2.
Just 2 equations, right? So we're going to look at the first guy, and we need to find his equation of his line, right? So we can use either our point slope, or we can use our slope intercept if we've got that and we can figure it out, or we can use when we have one point, right? So on this one, we don't have where it crosses the y, so we wouldn't be able to figure out the y intercept on that, not necessarily on it. Could we count what our slope is if we were looking at it between 2 values? So we know that the first value is at -2, 3. Where it's crossing the line is at -8, 0. Right? So we can find our slope. Correct? Visually, our slope should be what? Positive or negative?
Negative. Positive.
Well, we
positive.
go left to right. Positive. Positive, so we know to make sure it's positive. Now we can do it either way, right? We do 3 minus 0. 3 minus 0 gives us 3. -2 minus -8. -2 minus -8 is the same as -2 plus 8 gives us
-6.
6. Right? Because it's the same as 8 minus 2.
Oh, yeah, sorry.
-2 plus 8.
1/2.
Okay, so we have a slope of 1/2. Does it look like it's about 1/2? It's pretty shallow, right?
Yeah.
Okay, so here we have 1/2. Now we can find our equation of our line because we can say y minus y1 equals mx minus x1, correct? So now I know what my slope is. I'm going to replace m with 1/2. Now I'm going to pick a value to plug in. I like picking the ones that have the zeros, personally. Especially when when the y is 0. So if I plug in 0 here, I'm going to plug in -8 there. I'm going to say y is equal to 1/2 times x minus -8. Y is equal to 1/2 x plus 8. Now, can I leave? Is that slope intercept?
No.
No, because I still have a parentheses.
You can distribute.
When you distribute, y is equal to 1/2 x plus 4. Excellent. So I would write for this one, I might have f of x. Here's my first one. Y is equal to 1/2 x plus 4. I'm going to do a comma. You can do a comma, you can say if. There's a couple different ways. When what? When x is, now this is an open circle.
So it's not equal.
It's not equal to, are we using x's that are less than or x's that are greater than?
Less
Less than. X is less than what? What is our x value right there? On your graph. You see. So plug that down and just follow it all the way down to the x-axis.
It means -2.
What do you think it looks like? We're going to take our point where it's at.
Yeah.
We're going to go straight down on our x-axis.
Okay. Yeah.
What do we hit?
-2.
-2. So when x is less than -2.
Okay.
Okay. So for all values of x less than -2, we use 1/2 x plus 4. That line. Are we in agreement there?
Mm-hmm.
Yep.
Okay. So let's look at our other one. Can we figure out our other line? Do we have a y-intercept that we can
Yeah.
see? What is our y-intercept?
-3.
Okay. So when x is 0, y is -3. Okay. What does our slope look like?
It is.
Can we count it?
1, 2, 3, 4, 5, 6, 1, 2.
So find 2 points where maybe
It's
was
3, I think.
So whenever it was at -3, then we went up to, could you say that 1, 0?
Yeah.
1, 0 is here, right? So I could count up 3 over 1,
Mm-hmm.
right?
Yeah.
If we did our slope formula, we would have 0 minus -3, which gives us a positive 3. 1 minus 0 is 1, so we're still going to end up with it that way too. So we can say our slope, our n is 3, our b is -3. So this guy is y equals 3x minus 3. Right? Y equals mx plus b. We just plugged them in. So now I have 3x minus 3 when x is what? Which x values does this guy use? So we find our x-axis.
Anything greater than -2.
So he hits here at our -2.
But he's going down.
Well, it doesn't matter. We're looking at, is there a value? So we're asking a question.
Right.
If I pick a value on this x-axis, can I find a y for him?
Right.
Yes.
So it's anything greater than -2.
Anything greater than -2. Is -2 included in this graph?
Yeah.
Yes, because he's got a circle, a filled-in circle.
Or equal to.
Perfect. So there we go. We have our 2 equations. We were able to look at that one and say the first line is for x less than -2. The second line is for x is greater than -2.
Mm-hmm.
And we wrote our equations of our lines. Okay, makes sense? So for each of those, you're just going to write, and there's only 2. For each of them, we're just going to write the equations of our lines that we have on that. Okay? And we have a short time. We will see what we get through. Okay? We may adjust some stuff for next week again too. Right? Now, absolute value functions and transformations. This is all the same stuff. Okay? Same things that we were just doing. Basically, absolute value functions are 2 piecewise functions that just got put together. Okay, because what do we know about absolute value? we know that absolute value means that we have both a positive value and a negative value that give us an answer. So we have one equation and we have two equations. So it's two piecewise functions that we put together. We're saying when we have the negative values of x, what are the y values we get? And when we have the positive values of x, what are the y values that we get? That's all we have, okay? So a couple of things of vocabulary that we have for absolute value is an axis of symmetry. Okay, we learned in geometry that symmetry means we can fold it in half and it looks exactly the same on both sides. Okay, so it's the line that identically reflects the graph on it. And you should have a couple of things that we may end up looking at in here, okay? See if I can get this going for you guys. Absolute values are written as f of x is equal to the absolute value of x, right? That's all it is.
We're looking at this little page.
Little page, so that's the very first one.
Written as, it's the one we
Yeah, f of x at the very top.
Yeah.
F of x is equal to absolute value of x. That's all it is. Okay. So when we draw them, the graph will always look like a V. Okay? Why is that? Well, because we took this line, right? Because it was just a line, y equals x. We know that our parent function of y equals x looks like this.
Yes.
Everybody agree with me? 45-degree line, parent function, y equals x. But as soon as I made it into my negative x
It's just the
values,
exact same thing.
my y values are no longer negative. My y values are positive. So I took this portion of the line and said, oops, you gotta be, we just reflected it. He had to go up there because I have the same x values, but my y's are now positive. Okay, so he looks like a V, right? The point at the bottom is called the vertex. It is also called a turning point. This is also the same vocabulary we will use for quadratics. The turning point is called the vertex. Okay, it'll be the point either at the bottom or the top of it. Now, what's great about it is that we could add some extra things to this graph. We could add an A right in here in front of it. What do you think that A stands for? What has it stood for so far in all of our things?
It's not the x-intercept. Wait, no.
No, what is the A?
It's a variable.
Sometimes you've been seeing it as an M.
Oh.
So it's the slope.
It's the slope, right? So same thing.
I was thinking standard form.
Yeah.
So it tells us our slope, exactly the same. The coefficient of x will always tell us our slope. It'll tell us how steep or how shallow. Now, it depends, what will it do to the graph? Now, when we start out, we're going to look at the positive side. If I start out and my A is 3, so that means I would have like y equals 3x. I would say my slope is positive and it's really steep, right? Because my line would look like that.
Yeah. It's going up.
Now, do I get to use this bottom? No. He goes up this direction. So when my slope is higher, my graph gets skinnier. It gets closer together, right? That is actually called vertical stretch because they're looking at it along the y-axis and you're stretching it up higher. You're taking your parent function, you're stretching it up. Okay, so when it gets skinnier, write this down. When it gets skinnier, it is called vertical stretch. Okay. Now, if I had y equals 1/2 x, what would that do to my parent function?
It's gonna make it fatter.
Yeah, so a parent function, that means that that line would go this way.
Yeah.
Right? But I don't use this, he gets reflected up into the positive y values. Okay, so he opens up my graph, he makes him wider. If I was looking at this vertically, I've pushed it down, okay, so it's called compression, vertical compression. You will see those terms. I like to use skinnier and wider. It makes more sense to me. But you will often see the word stretch and compression, and I want to make sure that you understand those terms for it. Okay, so same exact thing. We're graphing, and we're basically, you will see it sometimes as a piecewise function for x values greater than where my vertex is, or x values less than, or the negative for it. So that's all that an absolute value function is, okay? So when we look at our parent function of it, and this is in your parent function part that you guys have, remember, it's just going to be that V line that goes straight up with our slope of 1, and then we're either going to pull our slope up skinnier or we're going to pull it wider.
Yeah.
Let's see, what time is it? Do we go right till 50 or is it 55? Do you know?
I actually don't know.
You think it's 50?
No, I think it's 55.
Okay.
Well, I'm not sure. I think it's 55.
Let me see what we have. Okay. When we have a value in front of our absolute value, okay, it is the slope. So it tells us all kinds of information. Okay, so if I had y equals negative x,
just be -1.
That would be that line, correct? Is my parent function?
Yeah, well, negative parent. Well,
that for my regular y equals negative x.
Yeah.
So now that when I have an absolute value, he goes that direction. So positive means he's tipped up like a cup. He can hold something. Negative, he's tipped upside down.
But it'll always be essentially the exact same on the other side, just going the opposite direction.
It is. It's always a V.
Okay.
Absolute values are always a V. Okay. So positive means we're up. Okay. So same thing. If my slope is -3, I'm going to have a skinnier one going down. If it's -1/2, I'm going to have a wider one going down. So all it does is tell us the direction. What's great is it's the exact same thing for quadratics. Positive means we're going up. Negative means we're going down. Okay, so what we're learning and what we are practicing in this is our foundation. Everything that we will do as we go on will be exactly the same. They will always move exactly the same for all of it, okay? And it's done. We're done. Is that how it works? Is that the end? That's not the end of it. What did I do?
Oh, you froze it maybe.
I might have frozen it. We will see. Let me see if I can't even get out of it. Well, there we go. Here, that way.
At least it didn't happen right in the middle of it.
At least we didn't have it in the middle of it. Okay, there we go. There we go. Okay, so I'm just going to show you a couple of these, and you will have an absolute value worksheet to work. What it does is, and actually that one will probably change for next week because transformations are so very important. Our book doesn't cover transformations because they assume that you've learned it in Algebra 1. But it is very, very important to me that we cover it right now in this section because it's going to make everything else that we do so much easier. So we're going to add a little bit into that. So make sure and watch your syllabus. I will probably still want you to go ahead and print it out and then just bring it next week and we'll work through it and finish it, okay? So in looking at our absolute value functions, if we were just to look at this one, they show some examples. You guys can always go into the slides. Here is our positive absolute value. If we had the negative one, he would be facing down this direction. We can find our values by plugging in any number that we wanted to, correct? So in this case, if we wanted to do a chart for x equals 1, we would go 5 minus 5, y is equal to 0. You know, so we can plot points. So if you're plotting, if on your homework it has you plotting for absolute values, just make a chart and then plot some points and fill them in for it, okay?
And we will address the rest of this form next week, and we're gonna talk about transformations for that.
Okay.
Right, you guys got it?
Yep.
Well done.
Give it a shot.